So welcome back to part 3 of these video tutorials on the June 2009 Regents, part A we're finishing up, and then we're going to move on to part B1. Okay, 29th has two waves that are approaching each other, one with an amplitude of 5 centimeters and one with an amplitude of 10 centimeters. These two waves are on the same side of equilibrium, so we expect them to constructively interfere, and when they are superimposed, they're on top of each other, so 10 plus 5 is going to get us 15 centimeters. Moving along here to number 30, sound waves strike glass, causing it to shatter. Okay, that is going to be a phenomenon we call resonance. Now, that is a definition. It's when the natural frequency of the sound wave, or excuse me, the natural frequency of the glass matches the frequency of the sound wave. It will resonate. Now, the particle consists of two protons, okay, and two neutrons. Neutrons are neutral, so no charge. So if we want to find the total charge, each proton has one elementary charge, so we're dealing with a +2 elementary charge. And then if we're going to be converting that to coulombs, okay, there's 1.6 e to the -19 coulombs in each elementary charge. So we multiply those two together, you get your 3.2 times 10 to the -19. An electron in the level of a mercury atom returns to the ground state. The photon energy could not be emitted by the atom during this process. Okay, so if we look at the energy levels of the mercury atom, okay, our n equals 1, our n equals 2, our n equals 3, and our n equals 4. Okay, we write down those corresponding energy levels. Okay, we're looking at mercury here. We have in the ground state minus 10.38 in the n equals 2 level. Okay, actually, excuse me, these are A, B, C, and D. The n equals B level is 5.74. N equals C level is 5.52, and so on and so forth, 9.5. So here's what I'm going to do. I'm going to look at all of these numbers. If they don't correspond to a number that is in between two energy levels, and it could be between any two energy levels, it can't happen. Okay? So, going through and looking at it, the only one that won't work is 4.64. Number 33, which phenomenon provides evidence that light has wave nature? So whenever you think of wave, think of diffraction. Waves diffract, okay? And we're talking about light. So the diffraction of the light through passing of a narrow opening is a wave property, and here's the answer. When Earth and the Moon are separated by a distance of 3.84 times 10 to the 8 meters, the magnitude of gravitational force between them is 2 times 10 to the 20th. What is the magnitude of the gravitational force of attraction of the Moon and Earth were separated by a distance of 1.92 times 10 to the 8? Now, there's a variety of different ways that you can go about doing this. You could just straightforward calculate. You have the mass of the Earth and the mass of the Moon in your reference tables, and you're given a new distance. But a little bit easier of a process to do it is you look at 3.84 times 10 to the 8 and 1.92. And if you figure out that and look at the ratio between them, you are cutting the distance in half. Okay, and if you cut the distance in half, the force must go up, but it's not going to go up by a factor of 2 like the distance. It's going to go up by a factor of 2 squared, aka it's going to quadruple the force. So if the original force is 2 times 10 to the 20th, the new force is going to be 8 times 10 to the 20th. But like I said, you can then look up the mass of the Earth, you can look up the mass of the Moon, and then go do the calculation with your new distance. But you know, you're going to be able to save some time if you do some proportional reasoning. This is a definition. This is what we just kind of were talking about in the last unit here, that the nucleus is held together. The gluons are the force carrier particles for the strong force. Electrostatically, they're repelling each other. Magnetism has nothing to do with it, so cross that off. And anything with mass does attract each other, but that is a weak force in comparison to the strong force. All right, so 36 starts our part B1 section. Okay, this is a estimation problem. The work done, so we know the work equals force times distance. So all we're looking for is the same order of magnitude. Um, One of the things that I would recommend knowing that an apple has roughly the weight of 1 Newton. So if you take 1 Newton and you move it through 1 meter, then you get 1 joule of work done, thus 1 joule of gravitational potential energy gained. Um, so 37, 38 is going to be based on this graph. What is the acceleration of the car at 5 seconds? Okay. Now, when we're looking at a velocity time graph, the slope is the acceleration and the area is the displacement. Okay, and I'm assuming, not even looking at these questions, that we're going to address those two. So the slope of a horizontal line, as you know, is 0. At from 4 to 6 seconds, the object moving at a constant velocity, aka the acceleration, is 0. Now, the next part is what is the total distance traveled during the 6 seconds? Well, I'm going to actually find the area of that triangle, and then I'm going to add that to the area of that rectangle. So we have 2 seconds times 10 meters, so we travel 20 meters in that 2-second interval, and then 1/2 base times height. Half the base is 2 times the height of 10 is also 20 meters. When we add the 2, we get 4 meters. Number 39 is the person weighing 785 newtons on the surface of the Earth weighing 298 newtons on the surface of Mars. What is the magnitude of the gravitational field strength? Okay, you have to ask yourself, what is going to stay the same when you go from the Earth to the Mars? And that answer is mass. So I can find the mass of the person on Earth because I know the weight, and I also know the gravitational field strength on Earth. Then I'm going to take that mass um, and then find G on Mars. So G on Mars would be the weight divided by that mass, okay, divided by M. And if you take that mu F of G, the 298 newtons, and you divide that by the mass that you came up with over there in the previous half, that the 785 newtons divided by the 9.81, if you do that in your calculator, you will end up getting the gravitational field strength of the moon, which would be 3.72 newtons per kilogram. A motorcycle being driven by on a dirt path hits a rock. If its 60-kilogram cyclist is projected over the handlebars at 20 meters per second into the haystack. If the cyclist is brought to rest in 0.5 seconds, the magnitude of the average force. So I got a lot of information there, so I'm going to start writing this out. I have an M of 60 kilograms. I have a velocity, initial velocity of 20 meters per second. I have brought to rest, so VF equals 0, in a time of 0.5 seconds, and I want to know the magnitude of the average force. So what I'm going to do, okay, and this is the one that students tend to forget about, is if you look at your reference tables, you have an equation that says J equals delta P. That tells me that an impulse is equal to the change in momentum. An impulse is defined as a force times a time. A change in momentum is a mass times a change in velocity. Our change in velocity is 20 meters per second. So if I'm trying to find the force, divide by t, my net force, average net force will be 60 times 20 divided by 0.5. So 60 times 20 is 120 divided by half, 240. Oh, sorry, 2,400, so 2,400. So 2.4 times 10 to the third. Number 41, okay, we have a force versus time, a displacement graph, and we're trying to look for the total work. So I look at my reference tables. Work is force times distance. Okay? Anytime you take a y-axis and you multiply it by the x-axis, what you're doing is trying to find the area underneath the line. Okay? So if I find that area underneath the line, I have 30 newtons times 4 meters. 30 times 40 is 120. Excuse me, 30 times 4 is 120. As the boy pushed the wagon, what happens to the wagon's energy? Well, they're doing work on it. In the first 4 seconds, it gains, well, it's going at a constant speed. So you ask yourself, okay, if it's not gaining speed, then where is all of that energy going? Okay, it's along a level sidewalk, so it's not gaining gravitational potential. So the only thing that must be increasing, okay, is, and the only reason you know this is because if it's going at a constant speed, then the applied force must equal friction force. So there must be friction. Is that the internal energy must be going up. Okay, it's not getting any faster. It's not getting any higher above the ground. There's no springs involved, so the only other choice is it must be gaining some internal energy. So which is the SI unit for work done? Well, that is a joule, which we know a joule because work equals force times displacement. So a joule is got to be equal to a newton times a meter, but a newton is a kilogram meter per second squared times a meter. So if I multiply those two together, I get kilogram meter squared divided by second squared. Number 44, we're having the momentum of a photon, P, is given by the equation P equals h over lambda, h is constant, lambda is the photon's wavelength, which equation correctly represents the energy of the photon in terms of momentum. So we have energy equals hf equals hc over lambda. So what I'm going to do is I'm going to play a little algebra game. I have momentum equals h over lambda. I see that lambda is connected between the two. Okay, so I'm going to solve this for lambda. So lambda equals h over the momentum, and I'm going to plug that in for that. So we have E equals hc over h over p. Okay, so I see the h's cancel out, and now I have 1 over p, c divided by 1 over p, copy, change, flip. That is p times c. So we look at our choices, and we get choice 4. The graphing one, number 45, if we're looking for current versus resistance, the constant potential difference is applied to a variable resistor held at a constant temperature. Which graph best represents the relationship between the resistance of the variable resistor and the current through it? So we're told that V is constant. So we know V equals IR, Ohm's law, right? And we're trying to compare I and R. So notice that they're on the same side of the equation. Whenever I'm trying to compare two variables, I want to put one variable on the opposite side. So I'm going to divide by R, and I have I equals V over R. And this gives me a better idea that I is by itself and R is in the denominator, meaning showing that it has inverse nature. If R goes up, I goes down, and an inverse graph looks like choice 1. Number 46, we have a 3 ohm and a 6 ohm resistor connected in series. I'm going to set up my VIRP graph, or chart, and R1, R2, and REQ. And this will just help me kind of sketch what I'm given, what I'm trying to find out. So we have a 3 ohm resistor and a 6 ohm resistor connected in series. So current through the 3 ohm resistor is 4 amps. The potential difference across the 6 ohm resistor. So if it's 4 amps through 3 ohm resistor, I know there's 4 amps everywhere in the circuit. And if I want to find V across the 6 ohm resistor, V equals IR. So I'm going to work this way. I'm going to take the 4 and multiply it by the 6 to get my 24 volts. Which combination of resistors has the smallest equivalent resistance? Well, this has got equivalent resistance 4, in series, so you say it 1. In parallel, This has an equivalent resistance of 1 over R equaling 1 over 2 plus 1 over 2. That gets us an R of 1. Here we have 1 over 1 plus 1 over 2. Excuse me, 1 over 1 equals 1 over R, and 1 plus 1 is 2. So 1 over R equals 2. So R equals 1 half. Okay, and then this has the equivalent resistance of 2. So this one, the smallest equivalent resistance is choice 3. And that's your part A and B1. I hope you found this useful. If you get some time and you want to then go on to the June 2010 Regents, we'll see you then. All right, take care. Bye-bye.